too many introductions, but I'll be the last one, I hope. So we will have this week two types of talks. We'll have the fellow talks, as Alistair already mentioned, and the main part of the program is the tutorials, in which our speakers will introduce the mathematics needed for doing the kind of applications that we are interested in, and the other talks will be on the applications themselves. Okay, I guess our first speaker will be Vinod Vaikuntanathan. Will tell us about the mathematics of lattices.
Oh yeah, I have.
High technology.
Yes, of course. Okay, so thanks Eyal for the introduction, and thanks Tal, Guy, Shafi, Eyal, everyone for putting this this workshop together, and Sanjam for. Thank you. So first of all, it's great to see all of you here. As Alistair said, this is a sort of an icebreaker, so let's just have a party together. You know, a party where you ask me questions and I answer. Right? It's a one-way communication. A strange kind of party. Okay, so the goal of this talk is to sort of, as an introduction to the mathematics of lattices, in particular, the mathematics of lattices as it pertains to cryptographic uses. So I'll be heavily biased towards the use of lattices in cryptography. So the thing is, you know, as most of you know, over the last 7-8 years, there has been a real explosion of so the use of lattices in cryptography, where we use it to construct all kinds of strange, interesting cryptographic objects. But to tell you the truth, really all these uses of cryptography, there are like 100 different cryptographic primitives that you can build from lattices, but all these rely on a small set of core techniques. I would say 4, maybe 5 core techniques. So my goal in today's talk is to tell you what these core techniques are, and I'll sleep happy if I get through, if it's not completely zero knowledge, if I get through, let's say, 1 or 2 to you. Okay, so that's the goal. So let's get started right from the beginning. Lattices, what are lattices? This is a lattice. It's a lattice. It's a two-dimensional lattice. And what is a lattice? I give you n linearly independent vectors in Rn. In fact, for today, all these vectors will be integer vectors for the moment. I don't want to deal with issues of rounding, precision, so on and so forth. So I give you n vectors from z to the n. And you take all integer linear combinations of these vectors, and that gives you a lattice. And that is that. Here you have b1 and b2. You take all linear integer combinations. You get things like, b1 plus b2, b1 minus 2b2. You can keep going, right? That gives you an infinite set of vectors. That's a lattice. Okay, great. So the thing about lattices, and that really is a birth of sort of hardness, cryptography based on lattices, is that the same lattice can be generated many different ways. So this is a basis for the lattice. It's a little bit of a different basis from what I showed you already before, right? So you take all integer combinations of b1 and b2, you get this lattice. And this is sort of a blue basis. It's a good basis. So why is it a good basis? Because these vectors are short, essentially as short as they can be, if you look at it. Again, you can generate the same lattice is also generated by other bases. This is an example. This is a pretty terrible basis, right? It is long vectors. They are skewed, they're close to each other, so on and so forth, right? So that's a bad basis. And we'll see what is the point of that's very nice, right? You have good and you have bad. It's not even particularly well defined at this point. Where is the line, right? We'll see what is the point of these good and bad bases as we go along, but just remember that there are these creatures. Okay. So let me ask you something. What about this basis? Is it good or bad? What do you think? Goodish. That's a good one. Goodish. What do you think? It's supposed to be a party. One doesn't make a party. Yes. It's not. It's not a basis. It's not a basis. Excellent, right? Because if you look at it, this guy cannot be generated as an integer linear combination of these two guys. A good way to see what is not a basis is you draw the parallelogram generated by these two vectors, that is this. Look at, see if there is a lattice vector inside. If there is one, there is no hope of generating that guy as an integer linear combination. That's that, right? So that is, this is not a basis. Thank you very much. Okay, so that's great. There are a lot of interesting quantities related to lattices that the mathematicians are interested in. I'll talk about just one of those today. And that will sort of translate to computation, that will translate to cryptography, right? That's sort of the source of all cryptography. Okay, good. So what is this problem? The quantity of interest in lattices is the length of the shortest vector in the lattice. Of course, it has to be a non-zero vector because 0 is always a lattice vector, right? It doesn't make any sense. Shortest non-zero vector, I call that lambda 1. Right? This is a fundamental quantity of interest in lattices. The gentleman there, anyone know who that is? The pop quiz, I mean, it looks like any other dude with a mustache, but but he's a very eminent mathematician. Is Hermann Minkowski, who really pioneered many of the sort of theorems in mathematics of lattices. So he was interested in this quantity. He proved various bounds on how long the shortest vector can be. So it says, if the lattice is dense, in the sense that if you look at the sort of the volume of the parallelepiped, you can bound the length of the shortest vector as a function of this this number. Okay, so on and so forth. Very nice theorems. We will only. This is as much as I'm going to say about Minkowski. I'll move on to sort of problems, computation, so on and so forth. So we are not just happy with knowing that there is a short vector in the lattice. We want to find it, right? That's what we do, computer scientists, right? We want to find it. And what that is the shortest vector problem. In other words, I'll give you a basis, and this basis has no bounds. I mean, it is an arbitrary basis of the lattice. It could be a bad basis, for all you know, right? A good basis contains short vectors, so not particularly interesting, right? I'll give you an arbitrary basis. The question is, can you find the shortest vector in the lattice? By the way, this creature is actually well defined. There is a notion of shortest vector because this is a discrete set. Because otherwise, what is, in R, what is the shortest, right? So well defined. Can you find it? That's the question. Right. This is believed to be a very, very hard question. Lots of people have worked on it. This is sort of the source of cryptography. Right. So, okay. So this example, you draw a ball around the origin, expand it till you hit a lattice point. That is the shortest vector, clearly. Okay, so we if we cannot solve something, we cannot throw the dart and it hits on the. We redraw the target, right? That's the approximate shortest vector problem. And say, well, I don't want the exact shortest vector. I want something that is at most 5 times a vector whose length is at most 5 times the length of the shortest vector. Okay, so that's the approximate shortest vector problem. Alpha approximation. Alpha could actually be a function of the dimension, for all you know. Right. That's the approximate version of the shortest vector problem. One more thing, and I'll get going, and that is a different problem called the shortest independent vectors problem. Okay, so what is this creature? Well, look, we found the shortest vector in the lattice, and that is this guy. Right? So let me ask you a question. What is the second shortest vector in the lattice? Right? I mean, I'm not happy with one. Give me the second. What would that be? Right? Think about it. Right? I say, well, look, this guy is the second shortest vector. Beautiful, right? Well, that's not an interesting second shortest vector. The interesting second shortest vector is one that is linearly independent from the first shortest vector, right? And that is, as it turns out, this guy, which is a little bit longer than the first one. Okay. More generally, I can define these quantities lambda 1, which is the length of the shortest vector, lambda 2, lambda 3, blah, 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 up to lambda n, which is the length of the nth shortest vector. And what does that mean? I take a ball around the origin. I keep expanding it. When I hit a lattice point, I know that is the shortest vector. That's the length of the shortest vector. Expanding it. What is the minimum radius by which I'll contain n linearly independent lattice vectors? Okay, the minimum radius that contains n linearly independent shortest vectors, and that's called lambda n. That's again a fundamental quantity in the study of lattices. Okay, and lambda 2 is 2 dimensions, right? Lambda 2 is this number. Okay, so the shortest independent vectors problem is given a basis of the lattice. Again, find n vectors, not one, but n vectors, each of whose length is at most lambda n. Right, that's the shortest independent vectors problem. If you think about it a little bit, I don't want to dwell on this point too much, but these two are distinct problems. If you solve one, it doesn't mean that you solve the other, right? Do you see why? Right, on the one hand, I'm asking you to find the shortest vector in the lattice. On the other hand, I'm asking you to find many, n instead of one, but they all can be as large as lambda n. Right? It may not contain a vector of length lambda 1. There's distinct problems, both interesting. Good. So that's as much as I'm going to say about hard problems. Okay, so once you have problems, you want to see what does it take to solve them. You know, approximate, exact, how much time, so on and so forth. So this is my one-slide summary of about 100 years of work, I suppose, on lattice algorithms and complexity. I'm doing a terrible injustice. Pardon me, but this is as much time as I'm going to get. Okay, this is really like 2 semesters worth of stuff in one slide. Okay, so we can ask, so what is this line? This is really the approximation factor, right? You start from left to the right, the approximation factor increases. The 1 is exact SVP. And what do we know about it? Well, it turns out that you go back all the way to Euclid, right? Everything good comes from the Greeks, yes? I mean, you've got to trace back, So Euclid, right? Euclid gave a shortest vector algorithm in 1 dimension. Okay, and what is, let me tell you, right? So here is a 1-dimensional lattice generated by 2 numbers, 6 and 8. What is the shortest vector in it? What does it mean, 6 and 8? All integer linear combinations of 6 and 8. That generates a lattice. What is the shortest vector in it? 2. Indeed, 2. Right? What is 2? 2 is the GCD of 6 and 8. Yes? So GCD is really the shortest vector problem in 1 dimension. So, and then it took about 1800 years before Gauss, and he said, well, 2 dimensions, I can still do it. Okay, that already took more ideas, more work. Just Euclid, right? Then it took more and more time. And the best algorithm we know at this point, and the work is still ongoing on this problem. It's very exciting work. Already in stock this year, there is a new, better shortest vector algorithm. But the best time we know that these algorithms run is 2 to the n. Okay, 2 to the n is actually exactly the, right, Noah? 2 to the n. Okay, good. 2 to the n is the best time we know at this point.
So, just to be picky,
yes.
Why do you exclude 0?
Well, 0 makes the problem uninteresting, right? I mean, I can always tell you 0.
No, GCD, like if you characterize it like a linear combination of integers, 0
yes.
will show up. So,
yes, but my
very nasty situation, not like how do you characterize it?
Not really. So my definition of the shortest vector problem excludes 0, right? I mean, so the definition of lambda 1 is, what is the shortest non-zero vector, right? So yeah, so I like 0, but I mean, we are Indians, right? I mean, we are very proud of our zeros, but for now, let's kind of leave it aside. Okay. So all right. So lots of work still ongoing, very exciting area, but the best known algorithm runs in 2 to the n time. So that's for exact. How about approximate? Once you sort of increase the approximation factor all the way, let's say, to 2 to the n over 2, right? 2 to the n, about 2 to the n. This is the groundbreaking, amazing work of Lenstra, and Lovash, who showed that you can, in polynomial time, you can find a vector whose length is 2 to the n over 2 times the shortest vector, the length of the shortest vector of the lattice. Right? This might sound, pointless to you. I mean, 2 to the n, I can do everything in time 2 to the n, right? I mean, what is there to do? The point is, this approximation factor does not depend. It only depends on the dimension. It does not depend on the length of the basis, or the bit length of the basis, which could actually be, of the input basis, which could actually be very long. You're saying, I don't really care. I can get an approximation factor that depends only on the dimensions. Beautiful, beautiful work. You can improve this a little bit to whatever this number is, n log log over log. Okay, that's the best known. In fact, you can interpolate between these two extremes, and you can get 2 to the k approximation in between in 2 to the about n over k time. Tilde hides log factors, right? 2 to the n over k time. And in fact, the interesting thing is this is the best known even if you have quantum computers, right? I mean, quantum computers don't seem to, achieve any speed up over classical algorithms. It's as far as we know. Right? Things could change, like tonight, for instance. But as of now, as far as I know, this is the best algorithm. Okay, so two extremes: polynomial time 2 to the n, and 2 to the n approximation, and 2 to the n time 1 approximation, exact. Okay, so that's algorithms. One could ask about the complexity of these questions, right? I mean, so, are these problems NP hard, right? I mean, in fact, more precisely are the decision versions of these problems NP hard, right? And that, it turns out, is the case. So in the exact shortest vector, whether I didn't say something very important, which is, what does it mean short? I mean, short, what does it mean? I have to define a norm, right? And we'll talk about the Euclidean norm all through this this talk. And things could change depending on which norm I'm talking about, but Euclid, right? Good for me. Okay, so the exact shortest vector problem is NP hard, turns out. And that's, again, a major sort of groundbreaking result of Vaikuntanathan back in the 90s. And so is it, and the NP hardness sort of stays even if you sort of increase the approximation factor. I mean, all the way up to something like 2 to the log n to the 1 minus epsilon. What is that creature? It's smaller than any polynomial, but very, very close to polynomial, right? Right? It's not n to the 0.000001, but smaller than that, but very close. Right, and that is NP hard. It's sort of NP hard under randomized reductions, so on and so forth, but let's not worry about it. Okay, so that's what we know about the complexity. Okay, so poly time, I can do 2 to the n. 2 to the log n to the 1 minus epsilon is NP hard. The really sort of exciting for us, for cryptographers, development came in the 90s, 96, with Itai discovering a way to construct one-way functions. The most basic, the most kind of structureless, the most primordial, cryptographic primitive that you can think of, starting from the hardness of approximating the shortest vector to within a factor of n. Okay, so that's what he did. It's a beautiful, it's a landmark result. Really, I mean, we exist. I mean, I exist because of this result, right? So look at this. I mean, there's a little bit of a conundrum here, right? So there's cryptography. Cryptography needs to assume that an approximate shortest vector is hard. Right? That's the best we know at this point. In fact, Itai started from something like n to the 6 or n to the 8. I'm not quite sure exactly what, but the later work of Michancho and Regev, beautiful work again, reduced this approximation factor to n, right? So it's better to sort of base cryptography on smaller and smaller approximation factors as it gets harder and harder. Right? It's better to move left for crypto. So that's what crypto is. That's what the NP hardness regime is, right? So there is this amazing open question in cryptography, which is, can you build any kind of cryptography from NP hardness? Right? So that's if you don't know it, you should know it, and if you are not working on it, you should work on it. Right? That's how important this is. So if I wasn't doing crypto back then, but I understand that one of the reasons people were so excited about lattice-based cryptography is that it gave us potentially one way to base cryptography on NP hardness, right? If you could sort of move this left, 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 if you move this right, 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 once they intersect, you're done, right? That's what we want. Unfortunately, life doesn't come so easy. Yes, so unfortunately, it turns out that n approximating the shortest vector is an NP co-NP, NP intersect co-NP. Right? It says that this guy wants the approximation factor is very important in deciding whether this problem has structure or not. Right? Less than 2 to the log n to the 1 minus epsilon, it doesn't have any structure because it's as hard as that. Right? And once you pass something like n, you start getting structure. Right? This is a result of Banachik back in '93, and this uses something called dual lattices, something called transference theorems. I won't get into it too much, but you should sort of Wikipedia it and learn. Right? It's a beautiful, beautiful result. So it says I can certify that a lattice does not have a particularly short vector in NP. I can give you a witness that tells you, right? I mean, how do you do that, right? Bizarre, but you can do it. Okay, that's NP co NP. You can extend this a little bit further. Beautiful results again. Aronov and Ragev extended this all the way to square root n. And if you move a little bit further, square root of n over log n, this problem is in co-AM, not quite co-NP, but sort of an interactive version of co-NP. Right? So that's where it stood. And what consequence is it that a problem is in NP intersect co-NP or NP intersect co-AM? The point is that, above this approximation factor and above, these problems, gap SVP with this approximation factor, is unlikely to be NP hard. Because if it is NP hard, then polynomial hierarchy comes collapsing down. Right? So in a sense, this sort of dashes all hope, one would think, but I have to take this with a pinch of salt, that you can base cryptography on NP hardness. Not yet, in any case. Yes.
That's because you can't move the red point.
Indeed. Excellent. You think right. Okay, good. So this says you cannot move the red point beyond this boundary. Who says you cannot move the blue point left of the boundary? Excellent. Please work on it. Okay, so this is incredibly important as a question. Yes?
But we don't have any negative results.
We don't have any negative results. No. No, not as far as I know. Right. So that is the algorithms and complexity slide. It's the only algorithms and complexity slide I have. So the rest of the talk I'm going to just ignore all the centuries of work on algorithms and complexity. I'm going to just talk about the crypto part of it, the crypto angle. So why lattice-based crypto? This is a mandatory slide that I have to put into every talk that I give about lattices, but let me do it anyway. Okay. So why lattices? Factoring breaks. In fact, we know that discrete logarithms can be solved in quasi-polynomial time on certain fields, right? So why not discrete logarithms in general? Why not factoring in general? Okay, that will be my dream situation, right? You will have to resort to lattices eventually. Quantum resistance, as I said before, quantum, you're dead with factoring and discrete logs and lattices. So far they stand. Worst case hardness. This is something that I'll get into in much more detail in the rest of the talk. Again, this is a unique feature of lattice-based cryptography. And again, really tons of applications. I mean, that you'll hear about today and tomorrow. Lots of things that you can do that we know how to do from lattices, but not from other things. Yes?
Quantum resistance, is there anything that is known that is different?
Not to my knowledge. Maybe you can get like a square root n speed up because of Grover type things, but I don't know any. I don't even know that actually. Okay, so what do I mean by worst case and average case, right? So this is really one of the core, very important features of lattices. Worst case hardness, all I talked about in complexity of lattices up to this point was worst case hardness. Right? So worst case hardness says there is one instance. For every algorithm, there is one instance where it fails, possibly. That's really the safest thing to assume, right? I mean, that's what complexity theorists assume. Whereas in cryptography, you need more. You need average case hardness. You need a random instance to be hard. Right, as we all know it. And fortunately, for lattice problems, worst case is equal to average case. So this is a very sort of broad strokes overstatement, and I'll get to the specifics in the rest of the talk. But you can get crypto systems assuming the worst case hardness of and approximating the shortest vectors, for instance. Right, this is not something that we know how to do from any other sort of mathematical object. Okay, so hardness is good. Average case hardness is even better, but we're not happy with that. We want to go from hardness to usefulness. Right? What can we do based on this average case hardness? And that is really the story of today, and hopefully the next talk and tomorrow. Right? You can build many things from lattices. Right? This is just a incomplete list of things, cryptographic objects and citations, you can do tons of things. And believe it or not, I want to tell you about all of these today in the next, 1.5 hours. The good thing about all these vast collection of these cryptographic objects is that you can really sort of distill a few techniques, lattice techniques, that enable you to build all these things in one shot. And these are the things. So number one, this notion of this is average case hard problem called the short integer solutions problem, and its cousin called the inhomogeneous short integer solutions problem, which has an unfortunate acronym. That's number one. And number two is the learning with errors problem. Right? So these are techniques that this gives you that, this gives you that. The third is a notion of trapdoors for lattices, and how do you generate them, how do you use them, right? That's number three. And number four, even better, right? So as you go down the list, the objects become harder and harder to construct and more useful, right? The last sort of technique that I want to tell you about is the notion of punctured trapdoors. Right, so we'll get to what all these things mean in a bit, but these are the four really core things, and if you know these, you are ready to go home and do your own lattice-based crypto. Okay. All right. So that's the goal for today. We'll see how far we get. I'll be very happy if I get to this. Okay, so before I tell you what I'm going to do, I also should tell you what I'm not going to do. Lattices have been used in cryptanalysis well before they were used in cryptography. I'm not going to talk about it. Beautiful, beautiful works. In fact, you can use lattices to break versions of RSA. Like amazing, very beautiful work. And I'm not going to tell you about it. I'm not going to tell you about special class of lattices called ideal lattices, although I think maybe Sanjam or Shai will get to it in their talks. I won't tell you about constructions of several other cryptographic primitives, pseudo-random functions, a fully homomorphic encryption, which Shai will get to, multilinear maps, which Sanjam will get to. So not too unhappy that I'm not going to talk about it. Okay, so that's that. Okay, so now let's actually get to the meat of things. Okay, so average case hard problems, short integer solutions. Okay, so here is the problem. Okay, so I give you a system of equations, and this is really good. This is an underdetermined system of equations, right? So you have three variables. R is a vector, three variables, two equations, right? And I want you to sort of find a solution to it. Easy, right? We all know. Thank you very much, Gauss. You do it, right? You do Gaussian elimination. You can find not just a solution, but essentially the subspace of all solutions. Okay. So now let me change this problem a tiny bit. Okay, this is really the core of hardness of lattice problems. So there are two types of problems you can define on lattices: purely algebraic problems. Decide if two bases generate the same lattice. You can do it, right? These are, you can do it. But once you introduce geometry into the picture, that's when things start getting hard. I'm not saying all sort of geometric problems in lattices are hard, but that's where the hardness, the source of hardness comes from. Okay, so short is a geometric notion. Can you find a short R? What do I mean by short? Let's say, an R which has 0, 1 entries for the moment, right? Could define this more generally. I could say, an R where the L2 norm of R is small, L infinity norm, so on and so forth.
Non-zero.
Indeed. Thank you. Short non-zero R. Good. And this turns out to be hard. This turns out to be insanely hard, and I'll talk about this for the next 20 minutes or so. Okay, so let's just be a little bit more precise. The short integer solutions problem is defined by parameters n, which is the number of equations, right, the height of this matrix. Q is the field over which I work. I'm always going to work over a finite field. M is the number of variables. M is the number of variables. N is the number of equations. Q is a finite field. And beta is a bound on the how short, right? I mean, what do I mean by short? I mean, how short a vector do I want as a solution? Right? So I give you a matrix A, of this nature from n by m. So this is an underdetermined system of equations, so it's always going to be, I don't know, short and a bit pudgy. And you have to find this short r. Okay. So that's it. A times r should be 0, so r is in the kernel of A, in a sense. The point is that there are many vectors in the kernel of A. This is an underdetermined system of equations. I want you to find a short one. Right? That's what it is. And again, one could talk about sort of many norms. What does it mean by short? You know, short L infinity, L2, so on and so forth. I'm just going to talk about L2. But really, you know, any norm, any reasonable norm you can think of, you know, you can. This problem is still hard, as far as I know. Okay, so this is the short integer solutions problem. So really, the way, I mean, you know, once you look at it, you realize that, you know, in contrast to something like factoring, which is parameterized by sort of one number, right? You know, n-bit, you know, something, you multiply the two, you factor. There are many parameters here, right? And that is sort of a, you know, an unfortunate sort of theme in cryptography. But let's kind of try to sort of at least isolate one of these, sort of merge two of these terms together. So really, you know, the q and the n, they don't really matter independently. All I'm talking about is really the group zq to the n, right? So I could cast the short integer solutions problem in a little bit more generality as a generalized SIS, which says I give you a bunch of group elements, right? So group elements here corresponded to vectors, columns of the matrix before. What was the group there? It was zq to the n, right? zq to the n. I give you many numbers, many group elements, and I want you to find a short linear combination, again, a short linear combination that sums to 0 over the group. Right? So really, q and n, they don't matter separately. All that matters is a group, which is q to the n. It's the size of the group, really, just q to the n. So it's one way to think about it. Right? I don't know how to whittle down any of the other terms, so I'm gonna really stop here.
Are you assuming that these guys are generators? They form generators of the group?
Good. So when I yes. So when I talk about zq to the n, I'm assuming that you know, this is a full rank matrix. So you can generate all numbers on the right hand side. For 0, it doesn't quite matter, but yeah, yes, indeed. Okay, so we'll go back. So this is, you know, this is just to give you some context. This generalized SIS, we won't talk about it ever again, so you don't have to remember it. This is the problem. Yes.
Can SVP be used to solve SIS or vice versa?
Yes, indeed, and we'll get to it. We'll get to so you know, so more broadly, the question you're asking, if I'm right, is this looks like a, you know, it looks like a nice algebraic problem. What does it have to do with lattices? Right? I mean, so why is this a lattice problem? What is the relation? We'll get to it. And you know, exercise, if you can figure it out in the next, I don't know, like 20 minutes, it's great. Right? This is really a lattice problem. This is really, SIS is a short vector problem on a certain lattice.
But you can think of like metric spaces over groups and all this kind of things, and you can frame everything in terms of algebra, no?
Well, okay, so maybe, but you know, the moment you sort of endow something with a norm,
you have a Hilbert space, like, or something, which is like, you know, vector general groups and algebras with a norm and things like that, and then you can characterize everything. I mean, it has nothing to do with lattices. I mean, are you saying it's because it's discrete? That probably is.
Discrete is a key thing, right? So when I said the group SIS, or generalized SIS, I was working over and I meant sort of a discrete group. I actually meant a discrete abelian group, but it doesn't have to be, right? But, you know, for the moment, just to give you some context, forget about generalization, right? Let's just focus on zq to the n as our group, right? So I give you a matrix, n by m matrix, short and fat. Give me a vector in the kernel, in the right kernel of this matrix, which is small, just small norm. That's it. Right? So that is what we'll talk about for the next 20 minutes. Okay, good, excellent. Okay, so the first thing you ask is why did I come up with this problem? Like, what's the point? What's the use for us as cryptographers? Right, so one thing that you can get out of this the hardness of this problem already is a one-way function. And this was essentially done by Itai's work in '96. I mean, he came up with this SIS problem. Why did he come up with it? He constructed a one-way function. And immediately after, Goldreich, Goldwasser, and Halevi observed that this same function is also a collision-resistant Nash function, even better, under the same assumption. So let's see how that actually works. So this is the first piece of crypto that I'm throwing at you. So please. Okay, so what is our function? What is our collision-resistant Nash function? It is simply this function. So f that takes as input, it's parameterized by a matrix A. So it's a family of functions, right? Parameterized by random, A's and ZQ to the n by m, full rank matrices for the moment. Takes as input a length m vector, r, and outputs A times r, mod q. So all I'm working with is over ZQ. All the operations are over ZQ. Okay, that makes sense? So it's a linear function, right? I mean, what good can a linear function be? I mean, linear functions are worthless. I mean, we like them, but they're worthless as cryptographic objects. And the point is that these are linear functions whose domains are restricted to be small sets, vectors of small norm, and that's really what gives it hardness. That's what SIS is, really, if you think about it. Right, so this is a function, this is a family of functions, and I claim it's a collision-resistant family of hash functions. Okay. In other words, if you find a collision, I'll show you a way to break SIS. Okay. So that's the point. First of all, I have to do something here, right? I mean, if m is too small compared to n, this is not even compressing. Right, so m has to be larger than, m is what is the description length of an element in the domain, has to be larger than the description length of an element in the range, which is n times log q, right? It's an element in ZQ to the n, so n log q. One has to be larger than the other for compression. So let's do it, right? So m is larger, a lot larger than n log q. And now, turns out that this guy is collision resistant. Why is that? Suppose someone can find a collision called r and r prime, right? A times r is equal to a times r prime mod q, let's say. R and r prime are both short. What is short? 0, 1 vectors, because that's how I defined my domain. Suppose this is the case. What do I know? I know that a times r minus r prime is 0 mod q. So in other words, r minus r prime is a solution to the SIS problem for A. I gave you a matrix A, you just found me r minus r prime, a short SIS solution. Why is it short? Because r and r prime have 0, 1 entries. Therefore, r minus r prime has 0, 1, maybe some minus 1 entries. Right? But it's still short. Compute the norm, it's at most square root of m, square root of the length. Done. Right? Very, very simple. So almost by definition, this problem actually gives you a collision-resistant Nash function. Right. So any questions? It's the first piece of crypto. Should be very excited. Okay. Good. All right. So this is it. This is collision resistant. Therefore, one-wayness. Right. Collision resistance implies one-wayness. So you're done. So interestingly, this function, we know about the hardness, even one-wayness of this function, only for the range of parameters where it's compressing. Right? So for collision resistance, it only makes sense to talk about compressing range of parameters. I mean, otherwise, what is collision resistance, right? But even the one-wayness of this object, we only know for the compressing range of parameters. Right? So there's something about SIS that is, I don't know, the hardness comes from the fact that there are many solutions, and the hard thing is to kind of pick out the small one out of it.
Is there any difference in terms of approximation parameter for one-wayness versus collision?
Not as far as I know. Not as far as I know. I mean, the proof of one-wayness goes through collision resistance. You know, that's the best proof I know. Right. Good. Okay. So that is crypto from SIS. Right. So it's the most basic piece of cryptography. Now let's see how hard is SIS. Right. So I just assumed I told you a lot about worst case hardness of problems. Lots of people studied SVP, SIVP, and so forth, and they showed NP hardness, so on and so forth. And here I assumed an average case problem and built crypto from it. There is a disconnect, yes. I mean, how do I bridge one versus the other? That's really, it's an amazing piece of work. I get goosebumps every time I think about it. This is really the start of cryptography from lattices, right? So this is the unique piece of worst case, average case connection that really non-trivial worst case, average case connection that I know. Very nice. Okay, so what do I want to do? What does it mean, worst case to average case? I want to show a reduction that does what? It gets a lattice basis. It gets any lattice basis, right? Long vectors, I don't really care. And it maps it to a random SIS instance. Right, a random matrix A, that is an SIS instance. And so, right, I do this, I give it to you, you solve the SIS problem. What does that mean? You come up with the vector E. I'm changing notations a little bit, I realize. So E and R, I mean, they're really all SIS solutions for the moment. So what does it mean, SIS solution? E is short, and A times E is 0 mod Q. Right? So you come up with an SIS solution. I am going to find a short vector in the lattice. Okay, that's what I want to do. In fact, I can do this many times. I can ask you for many SIS challenges. It doesn't have to be a CARP reduction. It could be a Turing reduction. It could be Cook reduction, Turing reduction, right? Of course, this reduction is randomized because, I'm supposed to generate a random instance. What am I going to do? So it has to toss coins. Okay, so that is what I want to do. This is the goal. How do I take any lattice basis and come up with one distribution, which is a uniform distribution on matrices, n by m matrices, such that if you solve this on the uniform distribution on the average, I can go back and find short vectors on any lattice. Right? That's really the core here. Okay. So one thing I didn't tell you, which I should have, is so what is this big deal about worst case to average case reductions? I mean, who cares, right? So the point is that factoring, right? I mean, what is the factoring assumption? Well, I don't know. I mean, one version of the factoring assumption says you pick two random primes of length n, equal size, multiply them, I give it to you, you give me the factorization, yes? But why two primes? Why not a prime of length n, another prime of length n plus 525? It's a different assumption all of a sudden. Maybe you can break one assumption but not the other. Who knows? What this gives you is it gives you one assumption, one distribution that is as hard as any other distribution. You solve it, you find a worst case solution. So that really is, in other words, the task of picking the right distribution, I don't have to worry about it anymore. This is the right distribution. That's it. That's the beauty of worst case, average case.
Don't spend too much time on it, but
yeah.
I think Yael commented this to me once, but how is it conceptually different from self-reducibility of discrete log, which is still totally cool, but gets less publicity somehow?
I love discrete log, as much as you do, maybe a little bit less, I don't know. But look, clearly less. But, the self-reducibility of discrete log is a little bit bogus, right? I mean, because the question is which group? I mean, so I know how to pick the discrete log instance. I pick at random, G and H at random, right? And that's good enough. But how about the group? Where do I come up with a group? I pick a random prime of length n, right? And that defines the quadratic reciprocity group or something like, or elliptic curve. I have a fixed way of picking an elliptic curve, and I assume that's hard. How about another distribution of elliptic curves? Who knows?
We're on the assume worst case, so because there are a few primes, but like anything which avoids known algorithms.
That's an assumption, right?
The same here. I mean, how do you pick Q here? The same.
Any lattice.
No, so the reduction tells you what the right Q is, and if you solve it for this Q, you solve any shortest vector problem.
I think the more fundamental thing is that it's NP hard. This Crypto is not NP hard. Right?
This is not NP hard either, actually, right? So I mean, I'd be very happy if it were. Yes. The point is that I can run, once you run the reduction, you know what the parameters are. You don't need to sort of assume hardness for the worst case Q, the worst case group, for instance. Yeah? Okay, offline. We'll fight it out. Okay, so let's do it. Okay, so let's show this worst case to average case reduction, Gaussian, right? Thank you very much. Right, this is a sort of a key character in our worst case to average case reduction, and we'll use Gaussians in the coins that I toss will be essentially to pick Gaussian distributions. Essentially. Okay, so this is a Gaussian, so is this, and so is it in n dimensions. Right, I can define n-dimensional Gaussian distributions, and you know what? I can also define other things. I can define. By the way, this is thanks to Oded, who knows how to code apparently. Okay, so these are Gaussians, but these are Gaussians on lattices. So what does that mean? I take a Gaussian with a certain standard deviation, right? So that is the number sigma that comes out of this probability density function, and I plop a Gaussian on each lattice point, right? So what does that mean? The probability density at any point is a summation of the density that comes from each lattice point. Right, so this is countably infinitely many lattice points. So it's not even clear that this is well defined, but it is. Trust me. And this defines actually a probability function. Okay, so that's yes.
How do you deal with the coin flips are just binary? So how do you deal with precision?
Okay, so this is again something that I'm totally going to ignore, totally slip it under the rug. But I'm going to sort of divide the space into sort of epsilon nets. Okay, so I'm not. Yes. For where the precision is polynomial in the dimension. So I have to be careful here, but okay. So this is another Gaussian, which is a little bit larger standard deviation, and this is yet another Gaussian, which is a little bit larger standard deviation, and quite soon you see that this actually becomes a flat distribution, statistically close to a uniform distribution once the standard deviation becomes large enough. And what is large enough? Large enough is quantified by this beautiful lemma of Michancho and Regev. They call it the smoothing lemma, which says that if I take a random lattice point, this is again, I'm being very informal here. What does it mean, a random lattice point? This random lattice point, okay? Plus, I'm going to add a Gaussian with standard deviation sigma, right? Which is what I just did. This gives you a distribution that is close to uniform, that is statistically close to uniform, as long as sigma is larger than the nth shortest length, lambda n, so length of the nth shortest vector of the lattice. Right? You have to think about it a little bit. Why is it lambda n? Why not lambda 1? Okay, why don't you just choose the Gaussian to be larger than lambda 1? Here is a counterexample. Here is a lattice, right? This is lambda 1. This is lambda 2. So clearly, if I choose a Gaussian, which is a ball really, with radius lambda 1, I'm not going to cover the entire space. I'm not going to get uniform. Really, the theorem says as long as you manage to choose it to be large enough, to be about the radius of this ball to be about square root n times lambda n, you are going to cover the entire space. In fact, you're going to cover it uniformly. Right? So you need something like that to even reach the sort of deep hole, the sort of the internal point of the parallelepiped. It says, that's the minimal thing. That's the sufficient thing. Okay, so this doesn't depend on the basis. It's an invariant of the lattice. It's a lattice invariant, right? So I give you a lattice that has a smoothing parameter, just like it has a shortest vector. It's the same. It's a quantity associated to a lattice. Okay, so that's Gaussians. What do I do now? All right, I have 5 minutes. Okay, so let's do the worst case average case reduction. Okay, so here's the basis. This is what I get as input. Could actually be pretty bad, but I just made life easier for me. What am I going to do? I have to generate many sort of SIS vectors, right? So how am I going to do it? And the first thing is I'm going to divide the space into q to the n partitions. This is an n-dimensional lattice, right? I can divide. This is essentially sort of take this vector, partition it into q parts. There's 3 parts, but in general q. Right? So this essentially defines a sublattice or rather a superlattice of this original lattice. That's the first thing I do, and that tells me what q is essentially, right? So q, there's no restriction on q. Q doesn't define a sort of a hard problem. Q only has to be large enough. Anything larger than a certain number is good enough, right? That tells me, it tells me sort of a lower bound on how fine-grained this division is. Okay, so that's the first thing I do. So far, so good. Okay, so I'm going to label lattice points, right? This point is 0, 0. This point is, 0, 1, right? Depends on which corner of the sublattice it falls into, right? So all points here, if I take them, their labels are going to cover q to the n, right? Can I write here? Oh, that's a terrible idea. Okay, well, never mind. So this is 0, 1, this is 0, 2, right? This is again 0, 0 because it's a lattice point. It's 1, 0, 1, 1, 1, 2, and so on and so forth. So it covers, there are q to the n many little dots inside a parallelogram here, and that covers q to the n. Okay, that starts sounding a little bit familiar now. So that's what do I want to generate? I want to generate q to the n. Point a vector from q to the n, and here it is, q to the n. Right? Now what do I do? I'm going to pick a random lattice point. Again, random lattice point, what does that mean? We won't I'll conveniently slip this under the rug. There is a very nice way of doing it. We'll talk about it at the end. Okay, random lattice point. Okay, so what is a random lattice point? This is a random lattice point. Okay, and once I pick I said all these things about Gaussians. Why did I say all these things about Gaussians? Because I'm going to use them. I pick this random lattice point and add a Gaussian error, a Gaussian sample around it. In other words, I pick a Gaussian, add it to this lattice point. In other words, I am actually sampling from that distribution with like many peaks that I showed you. So that is what that is. And now, let me make a simplifying assumption, a little bit of a simplifying assumption, which is that when I do this sampling, it actually falls at one of the corners of this finer lattice. Right? Why would that be? It probably won't, but let me assume it anyway. Okay, just to make my life easier. Okay, so that's what that is. Okay, so now this guy actually defines a number, a vector in q to the n, right? Because I said, remember, each corner in the final lattice can be labeled by a vector from q to the n, right? So that defines, once I get that yellow point, that defines a number, a vector in q to the n. I call it A1. Right? That's the first column of my SIS matrix. Why stop here? Let me do it again. Call it A2, do it again, independently at random, call it A3, so on and so forth. I do it m times. I repeat this process m times. I'm going to get m AIs. Now the beautiful thing is that if I choose my Gaussian to be large enough, how large? Lambda n, about lambda n, these AIs are distributed uniformly at random, right? Because I just sampled from the, the plopped Gaussian distribution. with a large enough deviation, which is random, so it's going to, the probability that it's going to land up at this corner is the same as the probability that it's going to land up at this corner. So it's uniformly random. Right? The AIs are uniformly random. And guess what? That is my SIS instance. Right? My SIS instance is A, which is A1 up to AM, where each of these guys is comes from this this process. Does that make sense? Makes sense. Okay, good. So I just generated a random SIS instance, which is, I mean, the algorithm I have, the SIS solver, will refuse to work if I feed it anything other than random. Okay, so I better do the right thing. Better feed it a random SIS instance, and that's what I'm going to do. Okay, and what is the oracle going to return to me? It's going to return a solution, high probability, and so on and so forth. And what is a solution? A short R, right? Say plus minus 1, 0, because that's what I need from the for the collision resistant hash. Right, so I get some Ri AI vector is 0 mod Q. That's what the oracle gives me. That's right there. Okay, so now the question is, what good is it? And now I'm supposed to find a short vector in my original lattice. The question is, how do I do it? 2 minutes, and I'll let you off. This is really the most, yeah. Okay, good. So let's sort of fix some notation. Vi is my lattice point. Yi is the sample that I got by adding a Gaussian to it, and E sub I is a short Gaussian, the difference between the two, which is short. Right? That's what it is. The key thing, the most important sort of thing that comes out of this reduction is the following. I claim that the sum of Ri Yi is a lattice vector. Is a vector in the original lattice, not this subdivided lattice. And that's the key. Because look at it, the Yi's themselves are not in the lattice, right? I mean, that's the whole point, and they're not in the lattice. But the dude, the SIS solver, just gave me a way to combine these Yi's that plopped into the lattice, that landed up in the lattice. And why is that the case? Well, okay, good. Well, maybe I'll just so what are these Yi's, right? So Yi's are lattice vectors with Yi's are vectors in space, where the coefficient when you write it down in terms of the basis is not an integer, but an integer divided by Q, right? Because I just took the lattice, I scaled it down by Q. So each Yi is Ri times is B times some what do I call it? Zi divided by Q. Right? That's what it is. And Zi is an integer vector. What did this dude just give me? What did this oracle just give me? He gave me a sum of Ri. So I just computed a sum of Ri Yi, which is a sum of Ri times this. But now the point is, if you look at the sum of Ri Zi, this is, I claim this is 0 mod Q. Right? That's exactly because it follows from the way I defined Zi's. Right? And therefore, this creature, the sum of Ri Zi over Q, is an integer vector. So this guy is a lattice vector. Right? So this is the key. The key is that to use the SIS oracle to tell you how to combine vectors that are not in the lattice and produce a vector that is in the lattice. And that is it. Yes, Tal.
I didn't understand why you needed to choose Vi at random and not just take one lattice point and sample the Gaussian around it.
Well, so the point is, I want uniformity in this. So essentially, what you say works, right? So So I don't need to sample a random lattice point. I just need to sample from a Gaussian centered at the origin, because if you pick a lattice point, why not pick the origin? And reduce it modulo the parallelepiped. Right? That's good enough. So what you're saying is correct, but I find it a little easier to sort of think about random lattice points, add Gaussian, and so forth. This is exactly the way to actually do the proof. Yes?
What happened to the error, the EI? Is that like, is the ZI over Q that's YI or that's BI?
The ZI over Q is the coefficient of YI. Right? So write YI as B times something. Right? So I can always write any vector in the space as B times something. And now I claim that because this YI lives in this subdivision of the parallelepiped, this something, B times that something, is a multiple of 1 over Q. Okay, that's how I actually construct it, right? So this is like 1/3, 2/3, so forth, right? So the claim is that this is YI, and when I write it in the basis of B, the coefficient is a multiple of 1 over Q. Okay, that's all I did. And how did I construct my AI? That was essentially ZI mod Q, right? I mean, ZI is an integer vector. Take this mod Q, and that was my AI, essentially. Right? Right, so let me just be more precise. So this is sum Ri. B times ZI is AI plus Q times some integer vector ZI prime over Q. Q kind of cancels off. It really is of no concern to me. The sum of Ri AI over Q, that's what you just solved for me. That is an integer vector. Right? So put together, this is B times some integer vector, which is a lattice point. Yes? Does that make sense?
Where we use the fact that the Gaussian isn't too large?
I haven't gotten there. Good question. Right? But, you know, at the very least, I have a lattice point, right? If I don't have it, I might as well stop and go home, right? Okay, so what does that mean, the sum of Ri, Yi? You know, Yi is V plus E, right? The sum of R times V is the sum of lattice points, which is a lattice point. This is a lattice vector also. This lattice vector minus this lattice vector is also a lattice vector, right? So bottom line, the sum of Ri Ei is a lattice vector. Yi is good, but it's sort of large. What is the use for me? The point is I want to get a short guy, right? And the point is that if I take not the sum of Yi's, but the sum of Ei's, that is also a lattice vector, because these guys differ. Ei and Yi differ by a lattice point. Yes? Makes sense? Good. Okay, so now I'm in business, right? So now I'm back to your question. This was a lattice vector that was good, but it's not a short lattice vector. It's somewhere out there. I don't like it, right? I want to get here. But if this is a lattice vector, this is also a lattice vector. And now I'm in business. So Ei are short vectors. How long? About lambda n. And the Ri's are in plus minus 1. So I'm adding up about n of these guys. So how long can this be? About n times lambda n. Right? And that's it. That's that. Yes?
Do you need to pick the v's at random so that this is non-zero with high probability?
Good. Excellent. Good point. So I got a short lattice vector. So I'm very happy. Again, go home, right? But what David is saying is, what if it's 0? Right? I mean, so you don't think about it very often, right? But this is a big problem. What if it's 0? Then I ended up doing all this work for nothing. Okay, so I'm not going to say very much about it. Yeah, so put this under technicalities. You guys actually figured out most of these things already. You cannot sample a uniformly random point. We'll actually work with not with the lattice, but essentially the parallelepiped of the lattice. Right? So this is something that I can sample from. David, what if this is 0? You can show that this is not the case, and really the key idea is that once I give you the Yi, right, the Gaussian is large enough that there are many possible lattice points where this could have come from. Right? So this is a pretty good lattice point, close lattice point. So is this guy, right? I mean, and once I give you these YIs, essentially, once I give the SIS oracle the YIs, it doesn't know where things are coming from.
Actually, going back to Tal's question earlier,
Okay.
which I was thinking, I think she suggested just picking a fixed V and taking Gaussian samples from around that V.
Yes.
And I think if you did that, then this would fail. This argument would fail at the end about getting a non-zero lattice vector. You're above the smoothing parameter.
No,
you don't need the
V's.
V's.
Being large enough. Never mind.
Yeah, I think it's.
It's not the point, it's the Gaussian around.
Don't think you need that. So really the way to do it is not do a random lattice point and so forth, but really sample from the origin as the center and reduce modulo the parallelepiped, and that works. Okay, so finally, I assumed, it's a big assumption, that when I sampled from the Gaussian, I actually got points from this finer grid. And this is never going to be the case, right? So you have some sort of a rounding, an additional rounding parameter, which you have to take care of, and it'll make your shortest vector not so shortest anymore. It'll sort of add to this. That's why you need Q to be large enough so that this splitting, this fineness, is so large that when you round, you don't add too much. If Q is 2, then you're really adding a lot to this. Okay, so finally, this is a theorem that you can prove that, for any parameters n, q, m, and beta with some conditions, so Q has to be large enough, you can reduce from worst case approximate SIVP to within a factor something like this, right? So square root n factor worse than the quality of the solution that the SIS guy gives me. Right, so you solve SIS and you give me a vector of length beta, I am going to find you in the lattice a vector of length, in fact many vectors, linearly independent vectors of length about beta times root n. And what does beta have to be? Beta is something like, beta is the standard deviation of the Gaussian, which is about lambda n times square root n, or the length of the vectors is lambda n times square root n. So you add them up, you're going to get something like lambda n times n. So the square root n and square root n add up, you get n. Okay, so this is in fact the best we know at this point, right? In other words, this is the best approximation factor we know for the hardness of SIS. Okay, the question is, so Daniel asked if you can do better, if you can move crypto, all the way to the left, and that is, as far as I know, still a very open question. Okay, so I did take a little bit longer than I thought, but not too much longer. So we'll move on later, but this is what we'll start.
Reconvene at 5 minutes after the hour.
You can ask me questions. You can grill me during the break.